Okay, so I'm going to do the last two together problems here. We're going to do 93 and 95 that we turned into together problems. Now, if you read 93, it says calculate the final concentrations of potassium and oxalate, barium, and bromide in a solution prepared by adding 0.100 liters of 0.200 molar potassium oxalate to 0.150 liters of 0.250 molar barium bromide. And they give you the KSP value for barium oxalate, okay, which is 2.3 times 10 to the negative 8th. Okay, so if we look up here, I've just scanned in the answers so I can talk you through it. Um, so now here we have 90, okay, for 93 it says the concentrations of ions are large, so Q will be greater than K. So here we have a position of where we can calculate Q because it's trying to reach equilibrium. Will be greater than KSP and barium oxalate, the solid will form. To solve this problem, we'll assume the precipitation reaction goes to completion, then we'll solve an equilibrium problem to get the actual concentrations. Okay, so first here are calculations of our initial amounts in millimoles. We just took the volume amounts, multiplying by the molarity to get the millimoles. Same molarity concentrate calculation we've been doing for a while. All right, and then we've got, this is the reverse of our KSP value. Okay, don't show this message, thank you. So since it's the reverse of the KSP value, it means that, no, it's not going to let me do that. Okay, it means that we're going to take the inverse of the KSP so that K is much, much larger than 1. Okay, because KSP is so small. All right, now, so if we go ahead and we do a stoichiometry chart, we've got our initial concentrations of both of them, and it's going to react completely. The oxalate's going to be our limiting reactant, so we only have 20 millimoles of that available. So when the whole thing is done, we're going to have 17.5 millimoles of barium and 20 millimoles of the solid. Okay, now, new initial concentrations. Okay, for barium, you've got, after the complete precipitation, okay, you've got barium, which is now going to be 7.00 times 10 to the negative second. Here's just our total volume down here, that's 250 mils. Then we're going to have, for potassium, the reason we had to multiply potassium by 2 is that potassium was up here, is that potassium was paired up with, what was it paired up with? It was paired up with oxalate. Oxalate's 2 minus, potassium's 1 plus, so we got to multiply that by 2. Same thing with bromide. Barium's a 2 plus, bromide's a 1 minus, so we got to multiply it by 2. So we've got our initial concentrations of potassium and bromide. Now for potassium and bromide, these are the final answers because they don't participate in a solubility product problem. So for potassium and bromide, these are our final concentrations, so we're good. Now for barium and oxalate, we have to do an ICE table or a KSP problem, and that's what I need to wrote my little note here to figure that out. We've got to do. So here is my ICE chart. Here's my KSP value that they gave me. We're starting with 0.070 molar. Now remember that we do not include the, let's see if it's going to let me, no. We do not include the, oh, there's the highlighter. The solid, nope, not going to work. Okay, they would not include the solid because it's a solid. So the only thing that we have to start with right here is the 0.0700. We're going to go ahead and get rid of the adding in the S so that our KSP value is equal to 0.0700S. And I guess the reason they use S, you can use X, you don't have to change it. We're talking about solubility, so that's why we sometimes will change it to the S value. Okay, so we solve for it. We get our S value equal to 3.3 times 10 to the negative 7th. Now, if you look at barium, if you add that to 0.0700, it doesn't change it. So barium is still 0.0700, but the oxalate, and this is really, if you think about it, the only thing that's different from what we did in Unit 4. Unit 4, we would have done solution stoichiometry to get here. It's just now we're doing the KSP to figure out how much oxalate we really would have in solution because it wouldn't be complete. So our oxalate is going to be 3.3 times 10 to the negative 7th moles per liter. Okay, and that's it. There's my final answers. So just like acid-base titration, it's a stoichiometry problem first, and then a KSP problem. Okay? All right, now 95 says a solution contains 1.0 times 10 to the negative fifth molar sodium phosphate. What is the minimum concentration of sodium nitrate that would cause precipitation of solid silver phosphate? Okay, so that's on the other side of it. Our KSP value here is 1.8 times 10 to the negative 18th. And again, these are solids that we normally might consider as insoluble, so that's why the KSP values are really, really, really small. Okay, so let's look at the background here. Here's our dissociation reaction. Silver phosphate is going to dissolve into three silvers and one phosphate. When Q is greater than KSP, the precipitation will occur. So we'll have to calculate the silver ion necessary for Q to be equal to K, and then any silver ion concentration greater than that will cause the precipitation to happen. So in this problem, we know the phosphate, we have an original amount. We've got 1.0 times 10 to the negative fifth. Okay, so that's what we're starting with. So we have to figure out how much silver we have to add in order to cause this to take place. Okay, so we do a KSP problem. We know the phosphate concentration. We've got K is equal to 1.8 times 10 to the negative 18th. We want Q to be equal to 1.8 times 10 to the negative 18th. We've got our initial concentration of silver, our initial concentration of phosphate, which we're going to plug in 1.0 times 10 to the negative fifth. So then we can solve for that, and this shows you a little bit of the algebra here. So our silver ion concentration, we take this entire thing to the 1/3 power, or you take the cube root of it, which gets us a silver ion concentration of 5.6 times 10 to the negative fifth, and then all we have to simply do is make a blanket statement of when silver ion concentration is greater than 5.6 times 10 to the negative fifth, precipitation of silver phosphate will occur. Okay, I hope that helps, and we'll do a lot of problems in class. Let me know if you have any questions.